Hello. As promised, I'm making an extra review video for you regarding calculating average atomic mass by isotope percentage. So this review video is for my in-class students and will also be helpful for my virtual students. And both should take a look at it. And please email me if you have any questions. I'm going to go over a couple of the assignments that we have done in class, and we've also discussed them in class, but I thought it'd be helpful to make a video for you in case you want to take a look at it once more. So I have a couple of PDFs here for you, and I'm going to go over both of them. I'm presenting my screen so you'll be able to follow along. So here's the first question. It asks you to calculate the average atomic mass for oxygen. And this is how you calculate the average atomic mass for the periodic table. So you take into account the isotopes of oxygen. And the table below is showing you that 99.76% of the oxygen is oxygen 16. That means if you go to the periodic table, I'll click on the periodic table here, I'll pull up oxygen. So oxygen has 8 protons, but you look at its atomic mass, it comes out to be 15.999, and it's not a rounded number because they calculate it using the average atomic mass based on the isotope percentages, how many isotopes are found in nature. So what we have here is so let me go back to our PDF. What we have here is a table showing you the percentages for oxygen 16. So 8 protons, 8 neutrons. That oxygen is found 99.76% in nature. And then 8 protons, 9 neutrons, oxygen 17, is found 0.04% in nature. And 8 protons and 10 neutrons, oxygen 18, is found 0.20% in nature. So if they say calculate the average atomic mass using these percentages, I'm going to just show you how to do that real quick. It's not a very complicated process. So here we go. There are a couple of ways to do it, and one of the simplest ways is to just take the individual percentages and the atomic mass for that isotope. So I'm going to take the 99.76% and I'm going to combine it with the atomic mass for oxygen 16. Then I'm going to take 0.04% and I'm going to combine it with 16.991%. I'm going to do the same thing for oxygen 18. The one thing I am going to do is the percentage. I'm going to go ahead and change that in advance. So instead of writing 99.76%, you guys know that 99.76% means 99.76 over 100, which is 0.9976. So I'm just going to go ahead and change the percentages right off the bat. So 0.9976. And that gets multiplied by 15.9949. And then you take the oxygen 17, and that's if you take 0.04 and divide it by 100, so it comes out to be 0.0004. 16.9991. And then finally, you take oxygen 18 into account, and you take 0.20%. So 0.20 divided by 100 is 0.002. 17.9992. And that's it. You just make sure you multiply these guys first and multiply this and multiply this and then add them all up. And you'll come up with the average atomic mass for oxygen. Now, the other way to do it is if you don't want to change the percentage into 0.9976 or 0.0004 or 0.002 and you want to leave it in there, that's fine too. You can say 99.76. It's just that at the end, you'll divide your final answer by 100. So you can do that division by 100 at the end, or you can do it at the beginning. So Now, do be careful. Make sure you put everything in the numerator in your calculator first, get a final answer, and then divide your final answer by 100. And that'll give you the average atomic mass. In the calculator, you have to be careful. If you just go ahead and put everything in the numerator and then hit the division sign and hit 100, it may just divide the last piece, the 0.20 times 17.9992 by 100 instead of the entire numerator. So you want to make sure you get your answer for the entire numerator first and then divide that answer by 100. So either case, both ways work. The top way works and the bottom way works. There are two ways to calculate the average atomic mass. And when you do that, then you'll come up with the average atomic mass that shows up on the periodic table, because you're taking into account all of the different isotopes of oxygen and their percentages with which they're found in nature. So hopefully that's helpful. And let's see if there is another question that I can do for you. So this one is just a simple question. It's asking you about magnesium. And I'll make the screen a little bit bigger. There we go. It says consider the individual atomic masses for magnesium isotopes. And so magnesium-24, 78.99% of the magnesium that's found in nature is magnesium-24. 10% of the magnesium that's found in nature is magnesium-25, and 11.01% of the magnesium that's found in nature is magnesium-26. So they ask you which isotope has an atomic mass closest to the average atomic mass listed to the periodic table. So you can take a look at the average atomic mass on the periodic table for magnesium, if you'd like to do so. But if you click here, you're going to find magnesium. Magnesium's average atomic mass is 24.305. So you can do it that way, and but the other way you can do it is simply by looking at the percentages, and you can say, well, magnesium-24 is the most abundant one in nature. Magnesium-24, you find 78.99% of all the magnesium is magnesium-24. So that's the one that's going to have the closest atomic mass to the average atomic mass that shows up on the periodic table. And the reason for that is because when you do the same equation I did for the previous problem, magnesium-24 will have the largest impact on the final answer because it has the largest percentage. So that's why its atomic mass will be closest to the average atomic mass that shows up on the periodic table for magnesium. All right, so the answer for that one is just magnesium-24. And give a mathematical reason for your part to part A. And the mathematical reason is simply if you put in the equation, and my light just turned off in my classroom. Give me 1 second. I'm going to trigger the sensor for it to turn back on. There it goes. So when they ask you for a mathematical reason, and you can put in the percentages, and you can come up with a mathematical reason by showing. We have the table showing in here. Okay, so you could say, well, Mr. Parvez, 78.99% times 23.9850 plus 10% times 24.9858 plus 11.01% times 25.9826. And then remember, when you get your final answer, you got to divide it by 100, right? So this answer that will come up, this average atomic mass that will show up, this average atomic mass will be the average atomic mass that shows up in the periodic table. And this guy right here is going to have the largest impact because it has the greatest percentage on the final answer. It's going to have the largest impact on the final answer. So you could write this equation down as your explanation for part B. And we discussed this in class. Same thing for boron. Boron has two naturally occurring isotopes, boron 10 and boron 11. If you go to the periodic table and you pull up boron, so boron's average atomic mass is 10.81. So if boron has two isotopes, one of them is boron 10 and the other is boron 11, then which one is found more abundant in nature? Well, it's boron 11. It's going to be found more abundant in nature because that's the one that then ends up having a larger impact when you calculate the average atomic mass, taking the percentages into account. That's why the number is closer to 11. 10.81 is closer to 11 than it is to 10. Now, if boron 10 and boron 11 were both found in equal amounts in nature, let's say 50% of the boron that you find in nature is boron 10, and 50% of the boron that you find in nature is boron 11, then on the periodic table, the average atomic mass would show up as 10.5, right in the middle of 10 and 11. But that's not the case. The average atomic mass comes up to be 10.81 because that answer was derived by taking into account the percentages of the isotopes that are found in nature, and boron 11 is found more abundant in nature than boron 10. That's why when you use the equation with the percentages and the average atomic masses of the isotopes, boron 11 has a more significant impact on the final answer. So hopefully that refreshes your memory as we discuss this in class also, but it's always good to have a video to reference. The other one we did was an assignment where I gave you the natural abundance information for oxygen. And I said, look, if you have the natural abundance information for oxygen, and let's say you find 1.0 times 10 to the 6 oxygen atoms in nature, which means 1 million oxygen atoms in nature, out of the 1 million that you found, based on the natural abundance information for oxygen, how many of those 1 million oxygen atoms would be oxygen 16 isotopes, and how many would be oxygen 17, and how many would be oxygen 18? So first of all, we want to reference one of our lessons right in the beginning of the school year, scientific notation. So this 1.0 times 10 to the 6, if you move the decimal 6 times to the right, your answer is going to be 1 million. So we're talking about 1 million oxygen atoms. All right, so if you find 1 million oxygen atoms in nature and 99.76% of them are oxygen 16, well, then how many of the 1 million are going to be oxygen 16? So you simply do a percentage, 99.76% times 1 million. That's a comma. And that will give you your answer for how many out of the 1 million will be oxygen 16. And if you want to find out how many will be oxygen 17, you take into account oxygen 17 is 0.04%. So you'll simply do 0.04%, which is 0.04 divided by 100 times the 1 million that you found that you were working with. And that's going to be your answer that goes into the second row. That's going to be how many out of the 1 million atoms, how many are oxygen 17? And of course, for oxygen 18, you do the same thing, except you're going to do 0.2% of the 1 million atoms. So the question was asking, look, if you have 1 million atoms, if you found 1 million atoms, based on the natural abundance information for oxygen, based on the fact that 90%, 99.76% of the oxygen in the world is oxygen 16, and 0.04% the oxygen found in nature is oxygen 17, and 0.2% of the oxygen found in nature is oxygen 18. Based on those percentages, out of the 1 million atoms of oxygen that you found, or the oxygen atoms that you're working with, how many of them would be oxygen 16, how many would be oxygen 17, and how many would be oxygen 18? So this is how you find them. Plugging it into the calculator, that is something that's just, elementary math. So you can do that on your own. So I hope this video is a refresher for items we've discussed in class before. If you have any follow-up questions, please send me an email or reach out to me so I can answer those questions for you.